So, all the equipment we use in the sleep lab to run sleep studies and titrations depends on electricity. Due to the nature of their chemical makeup, our brains and muscles operate with electrical impulses. With anything electrical, there are hazards and things we can do to mitigate such disasters before they occur. One of the nice things about working in the sleep lab, though, is they will have strategies to make the lab a safe environment to work in. And if you follow those, you should be okay. You're probably not going to understand most of the terms. We talked a little bit voltage, current, resistance, or ground. That's okay. We're going to talk more about that stuff in detail. We have to talk about safety first because before we can really get our hands dirty. I'll almost always refer to my special equipment and electricity rule in these presentations, which is 99.9% of the time when something's not working, it's not plugged in or not plugged in well. Sometimes all it takes to fix something is just push all the plugs in well, and that'll do it. There's only one set of information on the slide, and it's the most important one. Safety is everyone's responsibility. Take a minute and think before you do something. When I'm doing sleep stuff, I teach music lessons, and one time when I was packing up to go home, I was unplugging my laptop from the surge protector. It's kind of hard to get it out, and so I wrapped my hand around the surge protector where my computer is plugged in, and because it's a tough plug to get out, when I pulled it, an arc of electricity shot out from the prongs to my hand, and I got zapped, and it was not pleasant. If you've ever been tricked with one of those fake pins or touched an electric fence, you know how jarring that experience can be. Luckily, the surge protectors are alternating current instead of DC, direct current, and I was able to let go of the cord. We'll talk about the differences a little later, but alternating current basically turns off and on 60 times per second when DC is just a constant on one way. Because our muscles operate with electrical impulses, DC will cause your muscles to tighten and not let go of the cord, and then you cook. There are much bigger voltages and currents than a surge protector in the lab, especially when you talk about an amplifier. Long story short, protect yourself and others. If you're dealing with pediatrics, use electrical socket covers. Although the patient is capable of making decisions, you are more in control of a situation in a sleep lab, and you can limit access to equipment or rooms with high voltage equipment. If you ever get the nerve to try and repair electrical equipment, don't do it alone. If you are rendered unconscious from an electrical shock, you need someone else to call for help. Even if you aren't fixing something, equipment can have a short circuit or have leakage current which allows electricity to flow outside of the wire. Whenever working on something, unplug it or shut off the main power source first. You should consider every wire socket plug as live or hot until you determine that it is really not. Don't work with electricity when you're standing on a damp floor. Maybe you're on tile and the floor was just mopped. You just need to wait. Some things aren't even considered dangerous because electricity is such an integral part of our everyday activities. Because it's winter and we're laying on the fleece and wool and other long materials, we're creating static electricity when we walk and move around. I grabbed my phone charger cord last night and I got a nice shock, probably from all the extra layers I was wearing. When the heat's on, it makes the air less humid, and that creates a better environment for electricity to flow. Metal is a fantastic electrical conductor, so it's a good idea to take all metal jewelry off before doing electrical work. If you're really getting into the guts of the equipment, there are lockout boxes and other contraptions that you can use so that no one accidentally plugs it in when you're working on it. This thing right here, you can see. You got the wire to whatever device you're working on, and the plug is in this box, and it's locked so that no one else can use it. I think most of us has fallen victim to the phone charge cable that only works if the wire is bent to the left or right when it's plugged in. That's most likely because the wires inside have broken or severed, and they don't have a good connection anymore unless you contort it. That is a defective wire, and it really shouldn't be used, especially in bed where there are so many other combustible materials. Let's talk about fuses. We talked about it a little bit. What is a fuse? Let's say you have a super high-powered hair dryer that takes a lot of power. Between that hairdryer and the pure electricity coming from the street pole, there are two components that protect your equipment. There's a circuit breaker, or a fuse in the main electrical panel, and a fuse on the hairdryer plug. So what is that fuse? In order to protect equipment from too much power, there's a little piece of glass or plastic or something that has a small piece of metal that is rated to break or be destroyed at a certain voltage. And that ensures that the equipment is not damaged, and only if the fuse needs to be replaced to complete the circuit again. That's much cheaper than replacing the wire or the hairdryer completely. Your car has fuses as well. I've jump-started my car before, and I've done it twice. And both times I blew a fuse for the power steering. So when I got the car on, I couldn't really turn very well because the shock that I gave the car was too much to go through that fuse in it, and it was destroyed. Better that than the power steering equipment. Circuit breakers are another way to protect equipment, but not with fuses. It's a complex piece that can detect a power overload, and it has a disconnect circuit feature. And that allows you to go back to the panel and just flip the switch back, and it'll work again. Different equipment takes different levels of voltage and current, making them more or less dangerous. But we should always treat all equipment as if they are high voltage. Because of the differences in electricity amount needed for different things, you should always use the correct wires and cords for the equipment. Many times, I've just found an old adapter and used it because, well, it fit in the socket. I have also ruined a lot of equipment because I've done that, because the power was too much, or the current was, for the piece, and it would start to smoke. Not just power adapters, but all electrical wires. You know, Ethernet wires, like internet cords? We usually call those Cat 5 wires because they're arranged in a way that we call Category 5, or Cat 5. That is this right here. This is a straight through Category 5. And these connectors are called RJ45 connectors. They kind of look like when you used to attach a phone, like a wired phone, the old-timey kind, to the wall. That it was smaller than this, but those might have been a 22, but this is an RJ45. So those are Cat 5. They are 4 pairs of twisted wires, and what you can do is you can get the wire and this little plug, and you unravel each pair, and you have to shove them in to these little wire holders. That is so hard to do. I've probably done that 100 times, and it's so hard to get a good connection shoving those things in because there's not much leverage and those wires bend, and they can get out of order. So there are 4 pairs of 8 twisted wires, and they can all be oriented in different ways. And these wires do different things, like one is a ground, one is a hot wire. There are receiving and sending data wires. So if you plug these into something that receives an Ethernet cable, but not a Category 5 configuration, you can fry the equipment. We call the Cat 5 cables that are not made for internet patch cables. Some of the capnographs use these cables and have been fried because someone used an internet cable instead of a patch cable. So like this one here that's called a crossover, one of the wires is switched on one end instead of the other. These are for different pieces of equipment, and so if you got it wrong, you could have the hot wire going to the ground port, which is definitely not going to make it work very well. So read the manual on all this equipment and the information on the wire, because you need to absolutely make sure, unless you have hundreds of dollars, if not thousands, to replace it. There are 2 major classes of electrical hazards in the sleep lab, either through ignition or explosion of flammable or oxygen-enriched environments, or just plain getting electrocuted or shocked. The first is possible because of the potential of using supplementary oxygen for some of our respiratory patients. If there is a frayed wire or damaged equipment which could have current leakage, the oxygen content in a closed room can become so great that if a spark occurred, it could cause an explosion and a huge fire. There are three basic requirements for an ignition: a flammable material, which could be blankets, an ignition source like a spark, and oxygen, which is already in the air, if not more so from the oxygen concentrator. You can prevent these disasters by having good airflow to keep fumes from things like acetone or collodion out of the environment, because both of those are combustible. You can also keep certain equipment at least 5 feet above the operating level to isolate the two volatile components, gas and machinery. They'll be in semi-different environments. The other comes straight up exposure to electrical current, and that can come from touching something. Speaking of static electricity earlier, if your lab is washing the sheets and blankets, you should really consider using free and clear dryer sheets. Free and clear so that no patients are allergic, but dryer sheets because it will reduce the amount of static electricity on the sheets. If those things start to arc or make a spark, they can short circuit sleep equipment when the patient is moving around and connected to the wires. Later on in the course, we'll discuss all these issues and how they actually occur. When working in hospitals, the biggest electrical hazard is the ignition of gases or vapors from chemicals that can make a fire. A lot of these are caused by fault leakage or leakage current. Fault leakage is also known as leakage current. That means the electricity flows into the insulation surrounding the wire, which usually keeps the current inside the wire. When this leakage occurs, it can produce an arc, and when that arc hits something flammable, it can explode. There are a couple of different components to consider when thinking about electrical shocks. First, the pathway of the current through the body can determine whether a person has a serious or negligible injury. The heart conducts electricity from the right upper side to the left lower side. If you were to grab an electrical source with your right hand above your head, and the current flows through to your left foot, that follows the exact pathway of the heart's electricity and can really mess up the conduction. Secondly, we have to consider how much electricity are we being exposed to, a macro shock or a micro shock. A macro shock, the prefix macro being large or big, refers to a high current applied to the skin which is enough for the person to feel or even be injured or killed by. Microshocks are small electrical currents that you can't feel, but it's still enough to get through the skin towards the body tissues and fluids. The heart is the most susceptible organ to microshock, especially those outfitted with pacemakers. Here's a chart referring to the different levels of shock, and they're based around three components of electricity: amplitude, voltage, resistance, and current. I believe the first column is resistance, which is measured in ohms. I think voltage is the next, which are measured in volts, and the final number of the column refers to current, or amps, or amperes. We will talk about these three components and more, but know that the numbers are all related. When you increase the voltage, the other two numbers are also affected, and vice versa. As you can see, the higher the numbers of voltage and current potentially cause worse injury. Like we've talked about before, the more moisture in the air deters electrical conduction. When it's dry, it's easy for electricity to follow a path because the moisture in the air is not conducting the signal in all different directions. And that would disperse the electricity and just dissipate into entropy, nothingness. Therefore, keeping a humidification monitor and humidifier in the lab to keep the relative humidity above 50% is very helpful. Again, drying clear dryer sheets will also help the static electricity. We're going to talk more about grounding later and what it does, but basically grounding an electrical circuit means if there is leakage current or a problem with the wire, the electricity will go to ground, which eventually just leads to the earth. In any structure with electricity, there should always be one wire coming off the panel to a literal iron pole or stake buried deep into the ground. When we properly ground our equipment, there's less likely a chance of a disaster happening. However, there are times when we might have two power sources, like a battery-operated piece and one you plug into a wall. If you have more than one ground wire, that will create a ground loop, which is a new circuit involving the patient or equipment. and that's not good. So there should always be just one ground wire on the patient. This is not something you really have to think about because the hookup and all the stuff in the lab is taken care of for you. But if you eventually want to run your own lab or be a technical person like I was, you should understand the basics of grounding. Speaking of ground wires, we have those three-pronged plugs now, and the ground wire is that third prong that connects at the bottom. I used to play in a praise band at my old church, and I would play guitar and sometimes sing on the church microphone. The problem was the microphone was not grounded, and neither was my powerful tube amplifier, which made my guitar really loud. One time I grabbed the microphone while I was holding the guitar and got a real nice zap. When I was really young, I used an electric leaf blower to clean up my parents' yard, and it was the 90s, and so I would listen to my cassette tape Walkman. One time I was blasting leaves and listening to Limp Bizkit or something, and the Walkman in my pocket touched where the extension cord meets the leaf blower cable, and it shorted out and gave me another nice little jolt. It also flipped the circuit breaker inside. In this case, my Walkman was battery operated, which batteries are direct current, and the extension cord from the wall was operating on alternating current. When we talk about electrical circuits, we refer to them as being open or closed. Open circuits are incomplete and can't transmit power, and closed circuits refer to a loop that, when powered, can transmit continuously through that loop. And I used to get open and closed circuits mixed up because I thought, oh, an open circuit is open for electrons to flow, but that's not what it is. It's the wire, access to the wire has to be closed. We talked about that in the last one. Shock hazards only exist if the electrical circuit through the body is closed, or if two different power sources are used with a common ground. Device cables have a hot and a neutral wire, one that has power and the other that accepts power. When the neutral wire meets the hot wire, the neutral wire closes the circuit by directing the current to ground. Electricity is always searching for the terminator, or where it stops, and generally that follows the path of gravity towards ground. Not because of gravity, but that's just the way it flows. Because of ground wires, normal leaks just flow to the ground wire. If a ground wire is not on equipment or doesn't work properly, all those hazards potentially increase. Remember to follow your lab's policy and procedure manual. Those policies are there to keep you safe. You will most likely not be involved in electrical decisions or things, but you should notice if the electrical hookups are three-pronged or not. Again, grounding is already taken care of for you with the hookup. You don't have to worry about the patient being isolated from the electrical ground. However, you need to know in case something were to ever happen. All devices should have their own ground wire, that three prongs. If it doesn't have three, I wouldn't use it. Sometimes the third prong will fall out or can be taken off to fit two-pronged outlets, but I would not use them. Even without the ground prong, those wires will still work, but they are incredibly dangerous. Never used any wires that are frayed or that have been broken. Like I said, you're probably not going to be responsible for making sure all the equipment is connected to a common ground. That's usually handled before the lab opens during construction. But all electrical equipment is connected to a common ground, usually the lab's main power panel. The reason why having one ground is important is that different power sources may have different voltages that can cause a power disparity and an overflow to the equipment or patient. People with internal catheters may have saline in the catheter, which is an excellent conductor of electricity. So be careful with people who are older or might have pacemakers and catheters. If you know anything about the space program and when we went to the moon in the 60s, you might know about Apollo 1. Apollo 1 was the first spacecraft that was designed to go to the moon. And during a routine test of the spacecraft, a fire broke out in the cockpit of the command module, and the astronauts were killed. The cockpit was pressurized with 100% pure oxygen, 16 pounds per square inch, and it was determined that there was leakage current that ignited the oxygen and exploded. NASA was also responsible for developing Velcro, which was all over the command module to hold things down in the zero-gravity environment of space. When the oxygen ignited, the Velcro became the fuel that destroyed the spacecraft and killed the astronauts. Afterwards, a lot of safety measures were taken, including limiting the amount of Velcro in the command module and not using 100% oxygen during testing, as well as the high-quality standardization of installing and handling wires from then on. Although sleep labs are not pressurized with pure oxygen, patients are using supplementary oxygen, potentially in closed rooms, either through tanks or concentrators. We call these areas oxygen-enriched environments. Electricity protocols are super important when dealing with oxygen because of the volatile nature. First off, around smoking, no smoking. Smoking cigarettes or having a candle or open flames are absolutely not tolerated in the sleep lab. With all the oxygen around, it's very easy for a spark or ember from something burning to fall off and start a fire. I had one person try and burn sage to cleanse a room before. I put a stop to that really quickly. Patients love to bring in their own electrical devices, and those devices are notorious for causing something called 60 hertz artifact, especially heated blankets. And it's going to be 60 hertz artifact because when they plug in their device or whatever, in the United States, we have AC, which operates on 60 hertz. So that's the kind of interference you'll see. Heated blankets are not grounded, and they pose a significant fire risk. They're awful for artifact in the study, too. It's right on top of you in bed, also. That's an easy way to get the patient not to use it. Because they will absolutely beg you. If you just say it's a fire hazard and it will ruin the sleep study signal, which is true. When using chemicals like collodion or acetone, keep those in a firebox to prevent combustible materials from exploding, and don't use them with high concentrated oxygen environments. I've had one person that I hooked up for an MSLT with collodion, and unbeknownst to me, he took everything outside with that stuff on his head and smoked a cigarette. He could have exploded his head off. Collodion will go up so quickly. It was a miracle that nothing happened. All right. What to remember from these slides? Use grounded equipment and make sure that all of the grounding equipment is grounded. Always check for the wires for breaks, compromised insulation, and faulty prongs. Always remove additional electrical equipment from the patient during the study. If they're wearing a watch, if they're wearing, their headphones. Always maintain a proper humidity and use dryer sheets to mitigate static electricity. Store combustible chemicals away from oxygen and electrical sources, and never allow open flames run oxygen. Fairly simple stuff. Throughout this unit, we're going to be talking about safety stuff, but this is the bulk of it. We will have another slide presentation based on what happens to your body with different shocks, microshocks or macroshocks, and what that can do to you. So that'll be fun, right? Okay, see you next time.